Okay, so today we're going to talk about Bootstrap. I don't have this lecture posted online, nor do I have the code posted online, and that's because I was making some last-minute changes and I haven't finished all of that. So once I finish making all those changes, then I'll post it online. So anyway, on Monday we talked about randomization tests. Today we'll talk about something similar but different, and this is Bootstrap, okay? So bootstrapping, this term comes from that old phrase, to pull yourself up by your bootstraps, and origins of that phrase are disputed. One theory is that it comes from like a German folk tale where the hero got himself stuck in a swamp, and to get himself out of the swamp, he pulled himself out by his bootstraps, okay? And of course that's an absurd thing to do, and it only works if you're a folk hero. And it was, you know, for a long time it was used to just refer to doing something that was absurd to try to help your situation out. But somehow it has taken on the meaning that you work really hard and now you can fix everything. And maybe that's kind of a corruption of the original thing. But the original thing was like, you're working so hard, but you're not going to achieve anything because you're trying to do something impossible here. As far as statistics go, it's a resampling method that we're using to that we can use to test hypotheses or make conclusions about the population, and we're not going to use additional data, okay? And in some regards it does seem like we're cheating a little bit, or that this shouldn't work, but it turns out that, you know, people studied this from a mathematical perspective, and it's okay. It's okay to do this, all right? And we're going to kind of skip over the mathematical proof side of bootstrapping, and I hope that's okay with you guys. I'll just tell you the results of all of this is that there's certain times when you can do bootstrapping and certain times when you can't do bootstrapping, okay? I guess if we forced you to do a mathematical proof behind the bootstrapping, you would also come to that same conclusion, maybe have a deeper appreciation and understanding of all of that, but it's kind of hard, and I struggled with this stuff anyway, with the mathematical proving of these things, so I won't put you guys through that, okay? We'll talk about parametric and non-parametric bootstrap. Those are different. They're related, but they're different ways to handle this, okay? All right, and just to again highlight the difference between bootstrap resampling and the randomization test, all right? On Monday we talked about the randomization test, and we said you can use the randomization tests if your data came from an experiment where random assignment was used. If random assignment was used, then you should be using a randomization test. Okay, and that's when you can make cause and effect conclusions when random assignment was used. For bootstrap resampling, this is only going to work if your data comes from a random sample of the population. So your data needs to be selected at random from the population. If the population is not, if your data is not a random sample from the population, say it's from an experiment where you called for volunteers, so that is not a random sample, then you cannot do bootstrap resampling, okay? Bootstrap resampling requires that your data comes from a random sample, all right? And in both of these cases, we're using the computer to simulate this random process and the randomizing process to show us what the variation would look like if random chance is the sole source of the variation, right? Because whenever we do a hypothesis test, the null hypothesis is generally that, you know, the two groups have the same mean, but whenever we observe a difference, that difference came because of random sampling or because of random assignment, okay? And the alternative is that this random process is not the sole source of variation. So in all of these things, we're using the random process to get an idea of the amount of variation we might see. All right, for today's example, sorry for the wall of text here, our data is coming from our textbook. Our textbook uses, they looked at this study from the Center for Immigration Studies at the U.S. Census Bureau, okay? And they are looking at immigrants from Latin America. Okay, and Latin America includes Mexico, but a bunch of other countries in Latin America, Costa Rica, Guatemala, El Salvador, a whole bunch. And specifically, at least as far as this study goes, they are looking at the education achievement level of immigrants coming from Latin America. And the researchers have this question: is there a difference in the education achievement level of those coming from Mexico versus those coming from a different Latin American country? All right, this is the question that the researchers had in mind. We are taking data from the year 2000 census, and somehow the line got cut off at the bottom. But so we're taking data from the year 2000 census. We have a random sample of 150 Latino immigrants in Los Angeles. Okay, so we have a random sample of 150 people, and we're going to look at, and inside our data set we have a few columns here. One is achievement level, and that is the educational achievement level. This is going from a scale to 1 to 100. Beyond this, I don't actually have any details on what these numbers mean. Okay, we just know that on the low end is 1, on the high end is 100. If you graduate from high school, I have no idea what that number is supposed to be, but I'm imagining if you get, if you get your PhD or, MD degree, that's going to put you close to 100. And if you didn't attend grade school, that would put you close on the low end. But beyond that, I don't actually know what any of these numbers mean. So I apologize for that, okay? Other things we looked at is, or included in the data file that we're not really going to take a look at, is the year at which the immigrant arrived in the U.S., the age of the immigrant at the time they immigrated, whether the person is fluent in English or not, okay? And the one that we are interested in is whether this person came from Mexico or not, okay? We're going to give them a 1 if the person came from Mexico, 0 if the person did not come from Mexico. And so what we are interested in is there a relationship or some kind of link between education achievement level and whether the person came from Mexico or not? That's the research question that that our textbook has asked and what we're looking at. Okay, so the data file is available online. I have a link on CCLE to the book website. So you can follow those links. You go to the book website. One of the links will say data files and stuff like that. You click that, and one of them will be Latino Education CSV, and you can click and download the file there. Okay, depending on your browser, you might have to do right-click, save file as, or something like that to save it as a CSV, and you can load it into your computer. So let's take a look at this. This is not what I want. Okay, it's not what I want either. All right. So I have it saved on my computer, so I'm going to load that up here. Whoops, let me change my working directory. Set working directory to, we'll set it there, and now it will work. Okay, so I've loaded that up. If I take a look at the data file, this is what it looks like. We've got ID, achievement, so this is what we're interested in. And whether they are from Mexico or not, that's the other factor that we're interested in. Okay, and so I'm going to just load up dplyr, and I'm going to do, I'll just go ahead and type this out. What I want to do is I want to take our data file and feed it into group by, and we're going to group by whether they are from Mexico or not. Whoops. And then we're going to summarize and say we want the mean, and that's going to be the mean of the achievement column, and we want the standard deviation, and that's going to be the standard deviation of the achievement column. Okay, and this is what we have. So we have the mean education achievement level of those coming from Mexico. So Mexico 1, meaning they came from Mexico. That level is around 50. Here, let me slide this up so you guys can see without okay, is around 58.6. I have no idea what that means. And those coming from countries other than Mexico from Latin America, 64.5. Okay, And so as always in statistics, we're always asking the question, is this difference that we observed, is this a significant difference or not? Okay, we have an idea of the standard deviations that we observed here, and this is what it says, but really it's hard to see. Okay, I think it's a good idea to see actually how big our samples are. So we can just say, dimension Latino, we can see there's 150 rows, so we have 150 people, and I can do sum of Latino $Mexico, okay? And we see we have 116 people coming from Mexico, and if I ask how many are zeros, we see we have 34 people not from Mexico. Okay, so these are not huge samples. They're not tiny, but they're not huge samples either. Okay, we can take a look at some graphics. So I can do a box plot of achievement as explained by whether they are from Mexico or not. We'll do horizontal equals true, and our data will be our Latino data set. Okay, so this is hard to see, but we take a look at that. This is what it looks like. Okay, and you look at this and you go, well, is this difference significant or not? We see a difference, at least between the median values, but it's hard to come to a strong conclusion just from looking at the graphic. Okay. Okay, we can also do density plots. All right. So in ggplot, to do a density plot, we'll say we want our data set Latino. Okay. We're going to do our aesthetic mappings. What did I do? Okay. We're going to do our aesthetic mappings, and what we want to do is we want to create a density plot for achievement. Okay. And for the density plots, you don't actually need to map achievement to anything, but you do say this is what I do want to draw. And we want to take our color, the color of our density plot, and we're going to say we want that to be whether they are from Mexico or not. However, I've got to turn it into a factor because Mexico is stored as a 0 or 1, and ggplot will see this as numbers and not as a factor. So I have to say this is a factor, this is a categorical variable. So we do that, okay? And then I do plus geom underscore density. Okay? And this is what it looks like. Let me I want to put in some color here. So I'm going to just do fill is also going to be factor Mexico. And I'm going to, if I don't set an alpha thing, they're going to block each other. So alpha is kind of like a transparency thing. Okay, so we take a look at this, and this is a kind of a density estimation of the distribution, and we're looking at the green versus the pink, and I don't know. Is there a difference or not? It's a little hard to say, right? It's a little hard to say. Maybe there is a difference. I don't know. Okay, so anyway, we've seen that. Now we can, if we wanted to do a classical approach, we could use a t-test, right? So this would be a kind of classical method to compare group means. And that would be a t-test. Okay, t-test, when we do that, we get a t of 2.222, a p-value of 0.029, so about 3%, and this is what we have. And it says the mean of group 0 and the mean of group 1. That is what we observed. What are the assumptions that we're making when we run a t-test? You guys remember? So for t-test, we're assuming that the sampling distribution of the x bars come from a normal distribution, right? And we generally say that's okay as long as you have a large enough sample, and that seems, and our rule of thumb is samples of 30 or more are often big enough to make that assumption, and this is what so anyway, this is the results of the t-test. Okay, these put strong distributional assumptions on the distribution here. Okay. Okay, and let's so let me talk about bootstrapping. Let me just see, data exploratory analysis. That's what we have. Okay, so let me talk about parametric bootstrap. So with parametric bootstrap, we're going to test out kind of the null hypothesis, right? So in our scenarios, with parametric bootstrap, our null hypothesis is that the mean of group 1 is equal to the mean of group 2, right? So we can, we can say that we'll just arbitrarily say group 1 will be those people coming from Mexico, and group 2 will be those not from Mexico. This 102A. Okay, and if the null hypothesis were true, then all of our data being our 150 observations are coming from the same distribution, right? The same population. Okay? And in parametric bootstrap, we make the strong assumption that this population has some defined distribution, okay? So in parametric bootstrap, that this population, okay, we make the assumption that the population has some defined distribution. Okay, so practically that might be something like, basically if the null hypothesis were true, then all our data, all 150 points, or 150 people, come from, and we might say it comes from a normal distribution with mean mu and standard deviation sigma, okay? Or, depending on the problem, maybe you want to say, well, it's not going to be normal, it's coming from a Poisson distribution, or it's coming from a binomial distribution, or a beta distribution, okay? Whatever it is, in parametric bootstrap, you are saying that your data is coming from some defined, what we call a parametric distribution, right? A distribution that is defined by parameters such as mu and sigma, whatever that distribution may be. Now this is the hardest part in parametric bootstrap, is that perhaps this assumption is not true. If this assumption is not true, then you cannot hope for your data, your answers to be right, okay? On the other hand, when you do a t-test, you are making similar parametric assumptions about the populations, okay? So, parametric bootstrap is really, it's not any worse than the assumptions you'd be making for a t-test, okay? But there are still risks in making this kind of assumption, right? And if you said it's coming from, I don't know, a chi-squared distribution and that was way off, then of course your answers will be way off also. All right. So when you look at the density plot, this is what we have. Could this be representative of a normal distribution? Maybe. Okay. And it's always a little bit hard, right? Anytime you take a random sample from a normal distribution, it's not necessarily going to look normal, especially if you only have 34 observations in your sample. It's not going to necessarily look normal, and so there's a lot of kind of this judgment call that you've got to do, right? Okay, so this is what we have. Okay, so if the null hypothesis were true, all our data is coming from here. All right, so let's again think back what our p-value is. The p-value is the probability of observing our data, or something more extreme, if the null hypothesis were true. Okay, so the idea behind parametric bootstrap is we're going to create some kind of parent distribution here, and then we're going to simulate drawing data from it. And then we repeat this over and over and over again, and we're going to see how often do we get differences as big as the one we observed. Okay, can I flip the slide here? Some of you guys are still writing. Okay, so again, this is, in parametric bootstrap, this is what we're going to do. So, we take our data and we find the overall x bar and the overall standard deviation, okay? And we're going to plug those in as stand-ins for what mu and what sigma are for our normal distribution, okay? And then we draw a random sample random sample of 150 from the from there, okay? So we draw a random sample of 150 because under the null hypothesis, everybody's coming from the same population, right? Okay, and then we put 116 in group 1 and 34 in group 2. Because that's what our data looks like. Our data has 116 in group 1 and 34 in group 2. Okay? But if, again, the idea is that if the null hypothesis were true, all of our data, all 150 people, are coming from the same population. Okay? And then what we do is we find the mean of group 1, and then we find the mean of group 2, okay? And we calculate the difference between these two means. Okay. And we repeat this many, thousands of times. Okay, so we repeat this thousands of times, and then at the end we see how often did we end up with differences as large as the one we have or greater. Okay, and we estimate our p-value by finding how often we get, differences as large as the one we observed. So does this, I'm hoping this process makes sense. Okay. So again, the key, not the key, but the big assumption and I guess risk in parametric bootstrap is the kind of distributional assumption you're making about the population. Okay. But truth be told is that if you're going to do a classical approach to use a t-test or something like that, you're making just as strong assumptions here. Okay, so if we look at the overall, these are kind of our overall summary statistics for our Latino data set. Okay, is that the overall achievement for overall educational achievement has a value of 59.9 and a standard deviation of 15.24. All right, and so we're going to use these as the way to generate our data points using R's built-in random normal generator. Okay, and just so we know what the mean, just so we have a mean value for those coming from Mexico, that's 58.59. A mean for those not from Mexico is 64.5. That's what we have here. We've got, I just subsetted Latino achievement based on Latino Mexico or Mexican right there. And so our observed difference, I'm going to just say, is the absolute value between these two values. And so we have an observed difference of 5.92. Okay, so we're going to simulate a whole bunch of random samples. We're going to calculate differences ourselves, and we're going to see how often we get a difference of 5.92 or greater. Okay, so to do this, let me just show you one of these. Okay, I'm going to say random normal. Whoops. So basically, I'm going to just do random norm. And I say I want 150 values. I want 150 values, and the mean that I'm going to use is the mean coming from my data set. I'm going to take the mean of achievement, and then the standard deviation I'm going to use will be the standard deviation from my data set also. Okay, so I do this. This generates 150 values. And I'm going to take those, and I'm going to assign 116 of them to group 1. Okay, so that, I run that. I'm going to say just take 116 of them, assign that to group 1, take the remaining 34, assign that to group 2, and then I want to find, what's the mean of group 1, what's the mean of group 2. Okay, and we calculate a difference between the mean of group 1 minus the mean of group 2. Okay, and here I got a difference of negative 3.98. Okay, and the question is, how often will, and right here the only source of variation is the random sampling process, right? And so we're saying, how often, if random sampling is the only source of variation, how often will I get a mean difference as big as the one I observed, which was 5.9? Okay, so how often will I get a difference like this? And so, here I'm going to do 5,000 samples. We can do 10,000 samples. It doesn't matter. So I'm going to create a vector called difference. Do 10,000 of them. Okay. And then I wrap this up in a for loop with 10,000. So we run that. Okay, it's done. And we can say, okay, the summary here, and it says, the average mean difference was something around 0.04. The median mean difference is something around 0.02. So the average difference is very close to 0, as we would expect. The largest mean difference we got was 14. The smallest mean difference we got was negative 10. And we want to know, how often do we get mean differences of 5.9, right? I can kind of create a histogram of difference, okay? And we can kind of see, how often do we get a difference of 5.9 or something? And so it's, it's on the outer edges, but we'll see. And so for here, I can get an approximate p-value. I can take the absolute value of our difference vector. There's 10,000 of them. And we want to know how often is that absolute value greater than or equal to our observed difference. Okay? And if I just did this is going to give me a bunch of trues and falses, right? And so if I take the mean of this will just give me a proportion. Okay? And it says this happened about 4.7% of the time. When I took values, when I randomly sampled values from this normal distribution, where I've used the samples mean and the sample standard deviation as ways to generate these values, how often did I get differences of 5.9? That happened about 4.7% of the time. Okay, so this is just under 5%. So we might say, you know, we've got some evidence that there seems to be a difference in the level of education achievement between those coming from Mexico and those coming from other Latin American countries, although you know, it's not super strong evidence at the same time either. Okay, it's just barely under the 5% cutoff. Okay, so that is parametric bootstrap. Parametric bootstrap, you know, we're taking our data's overall. We use you know, these values from the data. To create our distribution. All right, let me talk about nonparametric bootstrap. Okay, in nonparametric bootstrap, we will not make any kind of assumptions about the shape or distribution of the population. Okay. So with nonparametric bootstrap, we do not make assumptions about the distribution of the population as far as the parameters of the population go. Say the key in nonparametric bootstrap is, you know, our data was obtained via random sampling. Okay, and so according to the laws of probability, because it's coming from random sampling, it should be to some degree representative of the population. Okay, so our data should be somewhat representative of the population. Okay, so in this case, if the null hypothesis were true, what we're saying is that, you know, here's, just imagine here's a box, this is my data, 150 points. You know, I've got 150 observations in here. We're saying if the null hypothesis were true, we're saying that all of this came from one population. Okay? That whether they came from Mexico or a different Latin American country, that actually has no bearing on their education achievement, because all of these things are coming from one population. Okay? That's what we're saying if the null hypothesis were true. Okay? And so if the null hypothesis were true, what we're going to do is we are going to use this as kind of a stand-in for the population. Okay? It's like we're making infinite copies of this data set. Okay? It's like we're taking this 150 points and we're going to just create like 1,000 or 1,000,000 copies of this, and we're going to say this is now my population. Okay? And, you know, I mean, that's kind of like what we have to do when this is all we have, right? This is pulling ourselves up out by our bootstraps here. Okay? So basically what we do is we sample from this with replacement. Okay? So we will we will sample 150 points with replacement. Okay. From our data, okay, right? Sampling with replacement is effectively taking our sample of 150 data points and then making like an infinite number of copies of it. And we're saying, now that I have an infinite number of copies of my thing, I'm now going to say that's my population, and I'm drawing data points from that. Does that kind of make sense? Okay, and it feels like, am I really allowed to do this? And the answer is yes, we can do this. All right, it's again, it requires that your data was obtained by random sampling. Okay, and if your data was obtained by random sampling, obviously, clearly, your population is not going to be just 1,000 copies of this thing, but this could stand in as kind of a pretend population here. Okay, so that's what we're going to do. So when we do non-parametric, and then we do the rest of the same thing. Okay, we sample 150 points. We put 116 in group 1, 34 in group 2. Find the mean. Find the mean. Okay, find the mean for each group. Calculate the difference and see how often these random samples produced a difference as great as the one we observed or something larger. Okay? Calculate the differences between means and then see how often our random samples produce differences as large as the one we observed. Okay, so let me put up the code here. So the code for non-parametric bootstrap is almost the same as the parametric bootstrap. The only key difference is the way we do our random sampling. Okay, so first I start off by taking the column of values Latino achievement. Okay, Latino education achievement, which is what we have. I'm calling this my pretend population. Okay, we don't really call this, we don't say that in bootstrapping, but that's effectively what it is. Okay, we're going to pretend that's our pretend population. We'll do this 10,000 times. Okay, and then for each replication, what I'm going to do is I'm going to sample from the pretend population, which is really just our data set. Okay, I'm going to sample from there. I'm going to take 150 values, and I'm doing it with replacement. So with replacement effectively makes an infinite number of copies of our thing as our population. So this gives me my random sample. I get group 1, I get group 2. I assign 116 to group 1, the other 34 to group 2, and then we calculate the difference between these. Okay, and we just do this over and over and over again, and we just see how often we get a value here. Okay, so we do this. Okay, and now to get a p-value, we're going to see how many times did our difference come out greater than or equal to the observed difference that we have. So we have an observed difference of 5.9. We can just look at head of kind of our difference vector, and we can see these are the different values that we observed. So we're observing differences of negative 3.8, differences of 5.02, and we want to know how often are these values, the absolute value of them, greater than or equal to the one that we have. Okay, and this happened, according to our random samples, this happened about 4.4% of the time. Okay, 4.3%. So a little bit less than 5%, a little bit lower than what we got from our parametric distribution. Okay, and so this would suggest that we have some evidence that there might be a link between whether the person came from Mexico or a different Latin American country and their level of education achievement. Okay, although that difference to begin with wasn't super great. Observed difference of 5.9. So it's just, is this significant? Could this have been a result of random chance? Maybe, maybe not. Okay, and that's kind of always our answer in statistics. But this is non-parametric and parametric bootstrap. We are not doing any kind of mathematical assumptions from the t distributions or things like that. We're just taking our data and either resampling it for non-parametric data or non-parametric bootstrap, or for parametric bootstrap we say I'm going to pretend that the population looks like this, and we do that. Okay, we will end there. Have a great Thanksgiving weekend. Have a good time. Drive home safely, wherever that might be, and we'll see you guys on Monday.